In 1950, physicist Enrico Fermi was having lunch with a few colleagues, casually chatting about aliens and flying saucers, when out of nowhere, he asked one simple question. Not a joke, not a setup, just genuinely, where is everybody? 75 years later, we still don't have a good answer. The universe is unimaginably big, unimaginably old, and packed with places life could exist. And as far as we can tell, we are completely alone in it. That gap between how likely alien life should be and how much evidence we actually have, which is zero, is called the Fermi paradox. Let's put actual numbers on this, because big universe doesn't really land until you hear it. Our galaxy alone has somewhere between 200 and 400 billion stars. Most of them have planets. And our galaxy is just one of roughly 2 trillion galaxies we can currently observe. Now add time to that. The universe is about 13.8 billion years old. Earth has only been around for 4.5 billion of those, which means there was plenty of time, billions of years of it, for some other civilization to show up long before us, get organized, and start spreading out. Even one, just one, anywhere, at any point in that enormous span, and yet silent. In 1961, an astronomer named Frank Drake tried to organize this problem into an actual equation. Multiply the rate of new stars forming by the fraction with planets, by the fraction that could support life, by the fraction where life actually shows up, by the fraction that gets smart, by the fraction that becomes detectable, by how long a civilization survives before it either destroys itself or just goes quiet. You multiply all of that together and you get an estimate of how many civilizations should be broadcasting right now. Here's the catch. Nobody agrees on the numbers. Some of those fractions we've barely started to measure, and a couple of them we're just guessing at. The Drake equation doesn't really give you an answer. It gives you a very organized shape for your ignorance. Here's the version of the paradox that actually keeps scientists up at night. You don't even need faster-than-light travel to colonize a galaxy. Slow, boring spacecraft, even ones creeping along at a tiny fraction of light speed, could cross the Milky Way and colonize it using self-replicating probes in something like 5 to 50 million years. That sounds huge, until you remember the galaxy is over 10,000 times older than that. 50 million years is a rounding error on a cosmic calendar, which means if intelligent, technological life were even moderately common, the galaxy should already be saturated with evidence of it. Old signals, old probes, old megastructures, something. Instead, we get radio silence, which is either really good news or really bad news, depending which explanation you believe. One popular explanation is the rare Earth hypothesis, the idea that simple microbial life might be common, but complex, intelligent life needed an almost absurd chain of coincidences to happen even once. The right kind of star, not too big, not too small, a stable orbit at exactly the right distance, a large moon happening to stabilize our axial tilt, plate tectonics recycling nutrients, a giant planet like Jupiter sweeping up dangerous asteroids before they hit us, and then evolution actually stumbling into intelligence, which on Earth took about 4 billion years and, by some arguments, was never guaranteed to happen at all. Under this theory, we're not special because we're first. We're special because we somehow won a lottery with a ridiculous number of tickets. This next one is the idea that genuinely unsettles people, called the Great Filter, proposed by economist Robin Hanson. The theory says, out of all the steps between lifeless chemistry and a civilization that spreads across the stars, at least one of those steps is incredibly, almost impossibly unlikely. A filter that nearly nothing gets through. The unsettling part isn't that the filter exists, it's that we don't know where it is. If the filter is behind us, something like the origin of life itself, or the jump from simple to complex cells, then congratulations, we already beat the odds, and the future's wide open. But if the filter is still ahead of us, some highly probable civilization-ending catastrophe that every intelligent species eventually runs into, then the fact that we haven't found anyone else isn't comforting, it's a warning. Here's a spookier option, borrowed from science fiction but taken semi-seriously by some actual scientists, called the dark forest hypothesis. The idea, the universe is silent not because it's empty, but because it's dangerous to be loud. Imagine every civilization is a hunter standing in a pitch-black forest. Announcing yourself, broadcasting your location in the galaxy, might be the single worst move a species can make, because you have no idea what's listening, or what it does to civilizations it finds. Under this theory, every intelligent species independently reaches the same conclusion. Stay quiet, stay hidden, which means the silence we observe isn't an absence of life, it's a room full of people trying very hard not to make a sound. A gentler theory is the zoo hypothesis, the idea that advanced civilizations know exactly where we are and are deliberately leaving us alone, the same way we try not to interfere with an isolated tribe or a protected nature reserve. Under this version, we're not alone, we're just not interesting enough to visit yet, which is somehow both comforting and a little bit insulting at the same time. And then there's the possibility that nobody did anything wrong and nobody's hiding. We might just be early. Red dwarf stars, the most common star type in the universe, can burn steadily for trillions of years, far longer than a star like our Sun, which means the era of the universe most friendly to long-lived, stable planetary systems might not even have started yet. On a cosmic timeline, showing up 13.8 billion years in might not make us average. It might make us almost absurdly early to the party, before most of the other guests have even been born. Now, we've gotten close to something exactly once. In 1977, a radio telescope in Ohio picked up a startlingly strong, narrowband signal from deep space, matching almost exactly what scientists expected an artificial transmission might look like. The astronomer who found it circled the printout and literally wrote "wow" next to it, which is now just what everyone calls it. It lasted 72 seconds. It has never repeated. Nobody has ever explained it. It sits in a file, unresolved, and the closest thing we have to a knock on the door, and nobody knows if it was a knock at all. Here's the strange part. Finding alien life, even old, dead, fossilized alien life, wouldn't just be exciting. It would be genuinely frightening. Because if we found evidence that life started somewhere else and then went extinct, that would suggest the Great Filter isn't behind civilizations like ours. It's still ahead. For everyone. Including us. Which means, in a strange twist, finding absolutely nothing out there again and again and again might actually be the best possible news we could get. So where is everybody? Honestly, nobody knows, and every explanation we have ranges from mildly humbling to deeply unsettling. Maybe we're freakishly lucky. Maybe we're being watched. Maybe we're early. Or maybe the universe is just a very large, very quiet room, and we haven't figured out yet whether that's because no one else showed up or because everyone else already learned to stay silent. Thanks for watching. If this one made you look up at the night sky a little differently, that means it worked. I'll see you in the next one.